Hi, Prof. My name is Xiao, and today I'll be presenting on our group project for BC3409. And our project is titled Price Tomorrow, which is a full stack web application that allows users to enter their desired instruments or tickers. And the application will use machine learning models to predict the price of the instrument for the next day. So my group mates are made up of Joshua, myself, Hao Zhi, and Guo Chuan, and we are from Year 4 Business and Computing. So firstly, I'll talk about the application tech stack, and then Guo Chen and Joshua will talk about the price prediction. Hao Zhi will be talking about the pairs trading implementation and limitations of our application, and also, of course, future extensions. So let's start with the business case. This application is motivated by two business cases. One of the observations that many people have made is that retail traders lose money. So this is statistically backed up. So according to research, taking the example of Forex, around less than 25% of Forex retail traders have losing accounts across 28 major Forex brokerages. So this is to say that if one were to start doing day trading or swing trading for Forex or other instruments, they are likely to lose money. So it's kind of like unprofitable to actually do it. And the second one is because we believe that machine learning for trading has been an increasingly popular field. But this is only so for machine learning techniques are mostly used in quantitative hedge funds or institutional investors, while we feel that it has poor access. Retail traders have poor access to machine learning to assist in their trading activities. So famous machine learning scientist Andrew Ng pointed out that ML has been very inaccessible outside of big tech due to the difficulty in implementation. So in order to bridge this gap between machine learning and retail traders, as well as helping them to have some kind of predictability power to lower the chances of them losing money, we hope to develop this web application to assist retail traders in their daily trading activities. So now I'll be moving on to talk about the application tech stack. So for the front end, we'll be using these four main libraries. So for the web framework, we decided to use React.js because it's a very popular JavaScript web framework that allows for reusability of components, and this makes our development process much easier. Furthermore, it also encapsulates a lot of the styling or designing needed. And Redux is for state management of the application, as well as querying the endpoints provided by our backend. For data visualization, we've been using AG-Grid to display tabular data and high charts to display time series data, these libraries are industry standards and highly used in financial institutions. So as mentioned earlier, our project title is Price Tomorrow, and we believe that the key focus should be prioritizing user experience. We want to make it as intuitive as possible since we are targeted at retail traders. And as you can see on the picture, we have a navigation bar on the right. Navigation bar which displays all the various instruments that users can trade. And this is all in a single page application. And as mentioned earlier, our visualization libraries follow industry standards. I think Hao Zhi will be demonstrating more later during the application demo. For the back end, we use Python because when contemplating whether to use JavaScript or Python, we realized that a lot of machine learning models use Python, so we thought that it would be easier if we use a Python backend. And we call the API service is built via a FastAPI, which is a lightweight API interface library in Python. And a lot of our data comes from Yahoo Finance. So yeah, our API adheres to Open API tree specification. So as you can see here, FastAPI actually, we can check the kind of endpoints just by adding /docs to the address provided by FastAPI. So this is quite convenient for us to check our work as well. So now Guo Chen and Joshua will be talking about the price prediction models. Thanks.
Thank you, Josiel. I'm Joshua, and I'll talk about the prediction models used in our project. Our group will be using 3 different models, namely ARIMA, LSTM, and random forest. The rationale behind choosing these 3 models is to give users a variety of models to choose from. ARIMA is a time series forecasting model, LSTM is a neural network model, and random forest is a decision tree model. The models take in the user input in a form of time period and the instrument that they are interested in. For all 3 models, we will calculate the root mean square error to compare how well they perform against each other. The mean square error calculates the average squared difference between the observed and predicted values from our model. Applying the square root on the MSE ensures that it is always a positive value. By using square root, we will also disproportionately penalize larger errors more compared to smaller errors. A higher RMSE value means that the model has poorer prediction capabilities, since it predicts a value that is further away from the actual value. RMSE is a convenient way for the users to compare these 3 models, as they use the same time frame of taking the past 7 days of prices to predict the next day's price. So comparing between models, the model with a lower RMSE is more accurate. Given that the users may have limited machine learning knowledge, using such a simple matrix can allow them to decide which models to use. And to standardize the implementation of our models, we also use a 70-30 split between our train and test set. However, the train test split is not done randomly since the data is time sensitive. We'll be using the first 70% of the data to train and the remaining 30% of the data to test. So the ARIMA model is our first chosen model. There have been several research studies on stock predictions that have been conducted on different solution techniques that are proposed over the years. And the more prominent techniques fall in 2 broad categories, namely statistical and soft computing techniques. The ARIMA model falls in the statistical technique, and it is commonly used in analysis and forecasting. It is widely regarded as the most efficient forecasting technique and is used extensively for time series. Due to its efficiency, we decided to first implement an ARIMA model because we want our model to quickly output a prediction in order to lower our loading time. And also, ARIMA model can be more robust and efficient than complex structural models in relation to short-term forecasting. So another reason why we choose ARIMA over other more complex artificial neural network models is because of our research in comparative studies between these 2 methods. So a work reported in neural network model versus ARIMA model in forecasting Korean stock price index compare the performance between ARIMA and ANN models in forecasting the Korean stock price index. And according to the studies, the ARIMA model generally provided more accurate forecasts than backpropagation neural networks. However, we must also consider the strengths of either ARIMA and ANN networks. ARIMA models generally perform better in prediction of linear time series, while ANN perform better in the prediction of non-linear time series. To supplement ARIMA's weakness of not being as robust as in predicting non-linear time series, we're also subsequently implementing an LSTM model, which Guoquan will talk about later. So the implementation of our ARIMA model is done via setting 3 different parameters, P, D, and Q. P is the number of autoregressive terms, or the number of lag observations in the model. D is the number of non-seasonal differences needed for stationarity. And Q is the number of lag forecast errors in the prediction equation, also known as the moving average window. So usually an extensive amount of steps need to be carried out in order to determine the best set of parameters for ARIMA. Firstly, we have to check if the time series is stationary. If it is not stationary, we have to use a model with trend or seasonality features. So for the ARIMA, one way to find the optimal parameters is by plotting the autocorrelation function, ACF, and the partial autocorrelation function, PACF graphs. The PACF graphs allows us to figure out the order of the autoregressive model, while the ACF helps us to figure out the order of the moving average model. In order to simplify the time series model, we are using a generic ARIMA with the PDQ values of 7, 1, and 0. This means that we are performing a different 7-order autoregressive model, and since stock price is subjected to seasonal stock trends at certain times of the year, we have to implement the differencing to make the time series stationary. Using an autoregressive term of 7 means that we are able to predict the next day price using the past 7 days. So our business case includes providing the user with enough information on the current instrument's closing price so that the user can make an informed decision when it comes to buying that instrument. And also, do remember that even fund managers cannot keep outperforming the market. Hence, we have to implement different machine learning models to supplement the user's knowledge on a specific instrument. And the ARIMA model that we have implemented takes the last 7 days of closing price data to predict the next day's closing price. We will also provide the train and test set RMSE to provide users with a performance metric. Users can then discern for themselves whether the current model has performed well enough based on their own risk appetite. Along with RMSE, we will show our model's predicted values and actual values based on the time frame that the user has selected for the specific instrument. This is additional information given to the user to allow them to make even more better, well-informed decisions. So next, Guoquan will take us through the LSTM and the random forest model.
Okay, thank you, Joshua. Now I'll be talking about our LSTM model. The basis in selecting our models is that we want to provide the user an all-rounded stock price prediction platform. While ARIMA models excel in predicting linear time series, we also want a non-linear model to cover the randomness of stock time series data. In the case of the stock market, the data usually is generated to be enormous and highly non-linear. To model dynamic data, we need models that are able to analyze hidden patterns and underlying dynamics, so that our application remains robust. With the introduction of LSTM, the analysis of time-dependent data has become more efficient. These types of networks have the capability of holding past information. So the intuition on why we chose LSTM over traditional RNNs and CNNs is because we want to make use of LSTM's unique cell state. The cell state acts like a conveyor belt of relevant information for each layer within the neural network. The gates within the LSTM cells allow for the LSTM structure to add or remove information to the cell state. Maintaining a cell state with relevant past information may prove to be invaluable should we set our rolling window to a longer period. We have implemented our LSTM with 50 units within our LSTM layer, along with a 30-day rolling window. Making use of the Adam optimizer, we will train our model on the input feature of closing price. However, our input feature had to be scaled. If we look at most stocks within the S&P 500, we generally see stocks with low volatility. But our application does not limit user selection to just within the S&P 500. Since the user can select any stock, cryptocurrency, or forex instrument, we want to make sure our LSTM network is robust enough to handle high volatility closing prices. As such, we will perform log and square root transformation on our training data. So how does all this help the user? Well, similar to the ARIMA model, we want to provide comprehensive information on a specific instrument to enable the user to make an informed decision. Our future prediction this time is based on 30 days of closing price data. ARIMA uses a 7-day window as compared to our LSTM's 30-day window. We want to play into the strengths of the LSTM model's cell state, hence the longer window period. With varying window length and models, the user is given different prediction prices. The user is able to discern which model they prefer based on RMSE and the visualization of predicted versus actual prices. So for our next model we have chosen is random forest. So why random forest? Random forest is a versatile model that can be used for both classification and regression tasks. Furthermore, it can also be used for time series modeling and forecasting in order to achieve better results. The main advantage of using random forests is that they do not require too much fine-tuning for reasonable results. This is important since the data used is actually taken from the live Y-Finance API, and it is dynamic and it fluctuates periodically. As such, we are able to avoid overfitting the model by using parameters that are fine-tuned based on a specific training data set. In addition, the ensemble of decision trees used in a random forest allows us to achieve a lower variance using a random subset of features. This ensemble learning method is not used by ARIMA or LSTM. So, random forest also allows us to determine feature importance by looking at the Gini importance and mean decrease in impurity. This allows us to measure how much the model accuracy decreases when the given variable is excluded. So, we will implement a sliding window where a series of consecutive inputs and expected outputs is shifted forward through time to use as samples for the supervised random forest learning model. Due to the time-sensitive data, we cannot do a random train test split. Instead, we'll be using a walk-forward validation where we split the data set into train and test set by selecting a cutoff point. In our case, where we are performing a one-step forecast, which means 1 day ahead, we'll evaluate the model by training on the training dataset and predicting the first step in the test dataset. We can then add the real observation from the test set to the training dataset, refit the model, then use the model to predict the second step in the test dataset. In order to have a one-step prediction for the entire test dataset, we have to repeat this process using multiple windows in the training dataset. This actually allows us to calculate the mean square error to evaluate the accuracy of the model. Similar to ARIMA and LSTM, Random Forest also aims to provide users with available and predicted price information on the instrument that they are interested in. Like the ARIMA model, we will be using 7 days of closing price to predict the next day's closing price. The RMSE value will also be displayed for the user to let them decide if they should use the Random Forest over the other models. Now I'll be passing my time over to Hao Zhi, who will be explaining about pairs trading.
Thank you, Coach. Now we're talking about pairs trading. So pairs trading is a market-neutral trading strategy that enables investors to profit regardless of the market conditions. So this is categorized as a statistical arbitrage or conversion trading strategy. And we'll be using k-means clustering and co-integration to help us obtain favorable ETF pairs to trade with. So k-means clustering is an unsupervised machine learning model that's used to identify the presence of subgroups within a dataset. Whereas in our case, co-integration simply means that the statistical properties between two assets are stable. So to do pair trading, we must first identify pairs of assets that have a tradable relationship. So first we have to generate pairs to test for co-integration. So this is usually done by grouping stocks into that belong to the same sector or the same industry. So the idea is that if these stocks were of companies that have similar industries and as a result, similar operations, their stocks should move similarly as well. However, this is usually not the case, as even though the stocks may be related on a fundamental level, but this doesn't mean that they provide a tradable relationship. So k-means clustering will help us group these assets into clusters, where these assets in each cluster are statistically related and can be tested for co-integration. And this will also help us to find non-traditional pairs for trading statistical arbitrage. So first, we will take a pair from each of the clusters after we run k-means clustering, and then we will test this pair for co-integration using the ADF test, and then we'll build a statistical arbitrage trading strategy using the pair. So using the stats model library, we have this co-in function, which will help us find the p-value and the critical value, as well as the test result for each of the pairs. And then we can calculate the H ratio for the position size via ordinary least squared regression. And then for each of the pairs, we check whether the p-value is less than 5% and the co-integration test result is more than the critical value. Then we will flag the pair as being co-integrated. Okay, and we're moving on to the app demo part. So hi there, welcome to the app demo part of the presentation. So here we are at the homepage of our web app. So basically there is some statistics for our asset classes. So for crypto, we can see we have stuff like the market cap, as well as the daily trading volume. And then for stocks, we have a few tickers here. And they basically show the market change value in terms of percentage and US dollars over the past day, as well as the yesterday closing price, and as well as the exchange that is listed on. So let's move on to the main feature. So it exists for all three of our asset classes: stocks, forex, and crypto. So let's take a look at the stock one first. So basically, our users will have to select a stock that they are interested in looking at, and then let's choose Apple here, and then they will choose a specific time period. So this time period will basically indicate how long the length of the time series data that we are feeding into the model. So next 6 months basically means we will show the Apple closing price 6 months ago to today's closing price. So as you can see, we get some stuff here that is popping up. So let's go through what they mean. So we can see the first blue box here is actually the closing price of today's Apple stock, as well as the closing price in yellow here. So we can see the boxes here. They show the daily percentage change as well as the weekly percentage change. And these boxes are actually color coded in a way such that if the change is positive, it will actually be shown in green. But if the change is negative, then there's a decrease, then the boxes will be in red instead. So let's take a look at our 4 graphs here. So looking at the first graph is basically just a price trend for Apple in the time period that we have selected. So we can see that the graphs are actually very interactive. If we hover over them, we can actually see the closing price for the specific date. And we can see that the other 3 graphs are actually the predicted prices of our 3 models, ARIMA, LSTM, and Random Forest. So we can see that for each of the graphs, we have plotted the predicted price based on the model, as well as the actual price for the asset in black. So we can see once again, if we hover over any part of the graph, we can see that, let's say, for example, here we can see is for 7 October, the predicted price was 144, whereas the actual price is 140. So all these models are generated based on the ticker that we have chosen, as well as the time period that we have chosen. So all these models, all these price predictions are actually generated in real time, and they're all relatively quick. So at the bottom, we can see some more information. So let's go through each of them. So we can see in the first column here, we have today's predicted closing price, tomorrow's predicted closing price by ARIMA, as well as the root mean square error. So basically this is the closing price for Apple for tomorrow for each of the models. And we can see once again is color coded in a way such that if the model predicts increase in price, it will be in green. But if the model predicts a drop in price, for example, LSTM predicts it will fall to 143, well, today's closing price was 153. So the box is indicated in red. And at the bottom, we also have the RMSE for each of the models. Basically, it gives our users a choice between more information between each of the models. So that's part of the reason why we use 3 models, is because maybe for different assets and for different time periods, certain models might outperform other models, and this can be calculated with the RMSE. So this will give our users more information and help them make a better decision in their investing choices. Okay, and we can see the same thing for Forex. It's exactly the same layout. We can just take a look here. So this is one of the ways that this is how we implemented the project. Basically, it allows us, it makes it very easy for us to include new asset classes. So for example, if we wanted to add a commodities asset class, we can just expand it here, and it will take very little time. So once again, we have the same models and the same predictions, and this time for different asset classes as well. And lastly, let's take a look at crypto. So we can see is the web page is very interactive because it actually shows us that when the model is running, it shows us this fetching icon, so that the users will at least know that their request is being processed and they are not left hanging. So yeah, same thing. If we wanted to add more models, it can be also easily done just by expanding the cards here. And if we add it to 1, we can. So if you add a new model, the change will be seen in all of our asset classes as well. Okay, so now let's move on to the last part of our web app, which is the pairs trading. So I mentioned pairs trading earlier. So this is the k-means cluster plot that we have came up with. And here we can see that for each of the clusters, the number of features or the number of data points. And this is the interesting part, which is our recommendations based on our models and calculations. So we can see that in this table, we have for each pair of asset of the ETFs, if the label is 1, it means that based on our models and predictions, or rather based on our statistical calculations, this pair of assets are actually co-integrated, and our users can use statistical arbitrage to make a gain on them. And then we also have pairs that are not co-integrated and will be labeled as 0. So that brings me to the end of the app demo. Thank you. Okay, so that was the live demo. Now I'll be moving on to the limitations and future extensions. So one of the limitations of our models is that they are all time series models. They are being used to predict market prices. But however, market price fluctuations could be due to external factors such as economical, social, political, or the prices of other assets. And as a result, if price fluctuations occur due to these other reasons, our model will not be able to accurately predict these fluctuations. And another thing for machine learning, for trading in general, there has been extensive research regarding trading strategies based on machine learning, and they often have poor performance on the actual markets, despite achieving a very high performance during testing. And this is likely due to overfitting of the model and also the inability of machine learning models to predict prices when there's black swan events such as the COVID-19 pandemic or the recent recession. So this brings me to our further extensions for our project. So one thing we could do to enhance our existing features is to obviously improve the accuracy of our models. And we can do that by optimizing the data fed into each individual assets. And we can do that with backtesting. So this will allow us to find technical flaws in our model and also improve user confidence in our prediction models. And we can also implement new features, as I mentioned during the demo. We could also add new models such as prediction based on sentimental analysis of social media data. And we also can add other asset classes as well. And to address the model limitation that I mentioned earlier, there's actually been research into a hybrid model using ARIMA and LSTM, and they have been shown to produce better prediction accuracy for stock prices, probably due to ARIMA being better for predicting linear relationships, whereas non-linear trends can be better predicted with LSTM. And that will bring me to the end of my group presentation. So thank you for your time.